Okay, well, binomial distributions are discrete random variables, and I know that discrete random variables have an expectation or a mean. E of x on mu is the mean, and a variance, which is also called sigma squared. Okay, so binomials do as well. Okay, and we have these formulas for the mean and variance of a binomial distribution. Okay, now remember that symbols x bar and sx and sx squared refer to sample data. So this is when I've just taken a few observations of a random variable and I've just actually worked with that small sample, relatively small sample of observations. It may even be a huge sample. These are still just x bar and sx and sx squared are still sample statistics. Mu and sigma squared and sigma are the corresponding things, but if I could run the experiment forever and see what things average out to in the long run, these are underlying properties of the distribution and never change. These ones are just properties of the particular sample. But mu, for example, is the distribution mean, or sometimes the population mean. This is the mean of all the things that ever could happen, not just the things that came in my sample. So sigma squared is the distribution or population variance, and sigma is the distribution or population standard deviation. Okay, so and watch out, we've got both variance and standard deviation knocking around. I might have to square root a variance to get a standard deviation, or square a standard deviation to get a variance. But the formula we've got here is for variance, not for standard deviation. Now these formulas here are in the formula book. Okay, they're simple, you can easily memorize them, but they are there to rely on in the exam on the formula book. Right, okay, so we're ready to do example 3.5, which is a childishly easy one once I've got the formulas. So I've got an n value of 3, I've got a p value of 1/4, so my expectation of x, also known as mu, the mean, okay, not an x bar, this is for the distribution, not just a sample, and my formula is np, so np equals 3 times 1/4 equals 0.75. Doesn't come easier than that. And the variance, not the standard deviation, is sigma squared, and the formula for that is, here we go, np1 minus p. np1 minus p. So I've already done the np bit, so we can be lazy and say 0.75 covers that bit, and 1 minus p is 1 minus 0.75 is 0.25, I can do it in my head, and then 0.75 times 0.25, cop out and do it on the calculator, and we get 3/16 or 0.1875. Easy peasy. Well, I say easy peasy, but actually I haven't finished, because this is the variance, and I was asked for the standard deviation. This is what I warned you about. Okay, we can all forget to square root things or square things. Which is it that I need to do? Well, this is sigma squared, is 0.1875. I want the standard deviation sigma, so I have to square root the 0.1875, which gives me 0.4330. So my actual answers that I need to double underline are the 0.75 and the 0.4330, and not the 0.1875. That was the variance, which wasn't what was asked for. So watch out, make sure that you remember to square root to find the standard deviation when that's what was asked for. Okay, let's push on and do this question in context. Okay, so this doesn't tell us it's binomial. How would we spot it's a binomial situation? Well, I have 30 people taking the test, and each one has a probability of passing. So as long as I'm counting the number of people who pass in a day, then I have a situation where I'm counting successes in 30 trials. Okay. So because the question hasn't done it, okay, this is like the table we had before. This could be binomial, but only if I'm counting the number passing. So I need to state that. I have done. And I need a value of n. My value of n is 30, because there are 30 trials, and the probability of success on each trial is 0.6. Okay, so I've done part A. So when they say define a probability distribution, or describe it, or name, you give the symbols, okay? You could write out in words it's a binomial with 30 trials and a probability of 0.6, but it's much more compact to write it this way. If you just say binomial, you won't get any marks. You've got to actually specify the parameters n and p as well. Okay, part B. Calculate the mean and standard deviation for this model. So we know that the mean is the expectation. Okay, which is the formula for that is mu, called mu, equals n times p. So NP is 30. Well, let's write the formula NP. So that's 30 times 0.6, which is 18. And my variance of x, which is sigma squared, is NP 1 minus p. Well, NP bit I've already done is the 18. 1 minus p is 0.4. 18 times 0.4 is 7.2. But that's variance, sigma squared. I'm asked for standard deviation. So sigma equals square root of 7.2, square root of my answer, square root of answer, that's what I type in, equals 2.683. 2.683. So there's my standard deviation. There's my mean. Underline them so the examiner can't miss them. Okay, and we've done part B. Now in part C, what's happening? An inspector's coming along and recording the number of passes. Good, that's what we'd expect. That's values of x. So but they're doing that on a large number of days. So they're observing x on loads of goes, okay, and they're finding the mean of those. So they've got, in part C, they've got an x bar. The mean of their observations from this random variable is that x bar is 19. Okay, and their observation is that their Sx, is it we're given? Yes, we've got a standard deviation equals 2.5. Okay, so what do we say about these? Well, 19 is the sample mean. The underlying expectation is 18. Okay, and they've got a sample standard deviation of 2.5, the underlying standard deviation should be 2.683. And we can see that both of these are a pretty good match. So when I comment on this, I must actually use the numbers as well as making the general comment in words. So that line there that I've just underlined the parts of, you can't miss that out. But the comment is the sample mean and standard deviation correspond well with the distribution, the theoretical distribution, the model I'm using for real life. The distribution mean and standard deviation match well with what was observed. Okay, so this is suggesting that the binomial model seems to work. Okay, well, why would the model not be appropriate? Well, there are assumptions for a binomial, and if you look at this, what it's not telling me, it is telling me there's a particular probability of passing, but the other assumption for a binomial, the one we so often have to write down, is the one about independence. Okay, if the people were not independent of each other in terms of whether they passed the test or not, then I wouldn't have a binomial model, and I wouldn't necessarily get such a good approximation here. So therefore, I can't say I've proved that the people are independent, but it seems quite likely that the people are independent of each other in terms of passing the test. Model appropriate, so it seems likely that the test passers are independent. So I've given a full comment on that.